Let's go over the principle of mathematical induction. So this is a method of proof for proving certain types of statements. It's quite useful for that. So we'll go through the principle, we'll give a proof for that, and we'll also give an example. So let's begin with, I guess, the definition, or I guess not the definition, I guess the principle in itself. So let's assume that so I'll just write this down. Assume that for each non-negative integer n, some statement, we call that P of n, so a statement P of n is given. So we need two conditions to hold. If they hold, or two, I guess, properties to hold. If they hold, then the principle says that P of n is a true statement. So the first property is that P of 0 is a true statement. And the second property says that whenever P of k is a true statement, P of k, let's go, whenever P of k is a true statement, then P of k plus 1 is also true. So just note that for the property B, this is only a statement about a conditional relationship. So if the statement P of k is true, then we say that the next, so P of k plus 1 is also true. So this is just a conditional relationship here. So if these two properties are satisfied, we say that then P of n is a true statement for every n in the natural numbers. So this is the principle of mathematical induction. Let's go over the proof. So the proof is quite long, and one reason for that is because we need what's called the well-ordering axiom. So we'll, I guess, write proof here. And I guess as part of the proof, we'll define the well-ordering axiom. So the well-ordering axiom says that every non-empty subset of n contains what's called a smallest element. So every non-empty subset of n the natural numbers, so we're including 0 here, so 0, 1, 2, and so on, contains a smallest element. So that's the axiom. So we'll leave that for now, and we'll visit it later on. So the proof begins by, so let's let S be the subset of N consisting of those integers let's call them J, for which the statement P of J is false, for which P of J is false. So now if S has nothing in it, so if S is the empty set, then our proof is complete. So since we're considering S to be the subset of N consisting of only those integers, for which P of J is false, so we're looking at, I guess, a set or a subset where we're considering the false statements. And if there are none, namely if S is empty, then we have proven what we want to show. Because we want to show, well, I guess we'll elaborate more on this as we go along. So if S is the empty set, let's just state that our proof would be complete. So what we're going to use now for this is, I guess, a proof by contradiction. So let's first assume S to be non-empty, because we're going against what we want to assume that S is non-empty first. So this is because we want to prove by contradiction. First assume S is non-empty. So that is, in mathematical notation, S is not the empty set. So now we're going to use the well-ordering axiom. So by the well-ordering axiom, the set S contains a smallest element. And if you think about the way we've constructed S, it's a subset, so it's still a set, and it's a subset of n, and it's a subset with integers. So if we're considering a set with integers, then the well-ordering axiom says that this subset contains a smallest element. So we know that S contains a smallest element. Let's call this element some value, some variable, not variable, some fixed symbol. Let's say beta. So since P beta is false, and it is false by the definition of S. So, or how we've defined S. So since P of beta is false, and since P of 0 is true, so if you look at property A in this principle, we assume that P of 0 is a true statement. So by property A, then we have that beta cannot be 0. So since beta is not 0, beta must be greater than or equal to 1. This is because b is a non-negative integer. And we could kind of rearrange this here and say that beta minus 1 is greater than or equal to 0. So another way to write this is beta minus 1 is an element of the natural numbers. Now, since for all beta in the natural numbers, we have that beta minus 1 is always going to be strictly less than beta. And we know that beta is the smallest element. In S. Then beta minus 1 cannot be in S. So we could write it like this: beta minus 1 is not an element of S. So let's continue now. So this implies the statement, so P of beta minus 1 must be true. Because if it wasn't true, it would be or beta minus 1 would be in the set S. So we can write otherwise beta minus 1 is in S. Now let's kind of, I guess, simplify our beta minus 1 here. So let's let K equal beta minus 1. And if you look at property B, so property B implies that so I'll just write this out. P of K plus 1, which is, in terms of beta, P of beta minus 1 plus 1, which equals P of beta. Is also a true statement. So let's look at the property again. So whenever P of K is a true statement, then P of K plus 1 is also true. So we assume these properties. So in this case, it means that P of beta is also a true statement. So let's go on the next page now. So since beta is an element of S, so we can write this, P of beta is false. We have a contradiction now. Which is what we are after in this proof. So let's, I guess, illuminate this contradiction. So P of beta is false. P of beta is true. Contradiction. So what does this? What's the consequence of this contradiction? So our assumption that S is non-empty, that was our initial assumption, cannot be true. And this implies that S is the empty set. Oh, let's take this out. This is what we were after. So this means that P of n, if you look at the final line in this in the principle here, so whenever these two properties A, B, are satisfied, we have that Pn is a true statement for every n in the natural numbers. And this completes the proof for the principle of mathematical induction. So basically for property B, we've assumed the truth of pk, and we do that to show whether P of k plus 1 is true. And we do this when we apply the principle of mathematical induction. So assuming the truth of pk to show the next number in the step, so P of k plus 1 is also true. So there's a name for this process, and it's called the induction hypothesis. So when we show that, what we're applying is the induction hypothesis. And there's, I guess, an alternative or alternate version of the principle of mathematical induction. So it's called the principle of strong, or sometimes called complete mathematical induction. So if you look at property B, the only difference is, so property B is replaced with the statement, whenever P of J is a true statement for all J. So I can write this down actually. So I'll just write principle of strong mathematical induction. So B goes to, so it's called strong mathematical induction because it works better for proving certain other types of statements in a stronger way, because you're showing, I guess, more things, or you're showing that something is true for a certain range of values J. So I'll just write this down. So whenever that's not. P of J is a true statement for all J such that 0 is less than or equal to J is less than T, so this is the range I'm referring to, then P of T, so this T here, is also true. So that's the only adjustment made when we alter the original principle of mathematical induction to make it stronger. So let's go over an example. So that was just kind of an aside, but for now let's go through an example where we have to use the principle of mathematical induction to prove a statement. Let's go over an example. So I'll just write a statement. So a set of n elements. So this is a general statement. Has 2 to the n elements. So we want to prove that this is true. So let's use the principle of mathematical induction to do so. So proof. So let's kind of give a name for this statement. So let's denote this statement, the statement above, by P of n. So where n is in the natural numbers. So I guess I should point out we can generate infinitely many statements. So if you look, this statement is in terms of n, so you could take any n, and because you can't exhaust the natural numbers, you can take infinitely many statements, and you can make a choice of an n value. So I could just write that as a note. So we can generate infinitely many statements. So yeah, one for each n. So the way we do this is we replace the n in the statement. So by any number, whichever number we're interested in. So to prove this example, so I guess it's a proposition. So this here, it's not that one there. Sorry, this one here. It's a let's call it a proposition. Let's prove this proposition. We need to show that this statement, so the statement Pn, as we've defined it, is true for all n in the natural numbers. So P of n is a true statement for all n in the natural numbers. So if it's true for all n in n, it's just a true statement, pretty much. Take any n you like, and it's we show that we prove the truth for all n in n. Then it's hard to argue with the proposition. So let's go ahead with that. So if you look at the principle of mathematical induction, so we now we've already proved it. Let's use it now. So if you look at properties A and B, we'll start off with the property A. So P of 0 is a true statement. So if n is 0, we have 0 elements in the set. So let's show that. And therefore so if n is 0, what are we saying? So a set of 0 elements has 2 to the 0. So it has one element. So if you think the only subset of the empty set is itself. So we know that the empty set is a subset of every set you could possibly think of. So if you think about the empty set itself, the only subset of that is the empty set itself. Just make an asterisk in the only. So what does this mean? So if you consider P of 0, so let's write this out. A set of 0 elements has 2 to the 0, which equals 1. So that's true because of this. So that's what we'd like to show. So we've satisfied the property A. Very good. Now let's move on to verifying property B. So let's, I guess, write down what we need to show. So we have to assume the truth of the statement, or of the following statement. P of k, which is, so we're replacing n by k, a set of k elements has 2 to the k subsets. So we've assumed that this statement is true, and as we do it at this point, we use what's called the induction hypothesis to prove that the next statement, so P of k plus 1, is true as well. So I guess next one, P of k plus 1. Okay, let's begin. So let's say y be, so early on here where it's going to be quite ambiguous what we're doing as we go through it. Hope you may appreciate, I guess, the method that we're trying to use. So let's let y be any set of k plus 1 elements. So any set with that many elements. And let's choose an element in this set, and let's give it a name. Let's say it's y0. Now let's consider all the subsets of this set. And we can observe that every subset, it either contains that element or it doesn't. That exhausts all the possible, combinations of subsets we can have, with the condition that it either contains the element y0 that we've chosen or it does not. Now, first we'll consider those subsets that do not contain y0. So we can, label these. So these are the subsets of y, but we have to take out this element y0. So we can observe that, this set here, y minus y0, has one fewer, namely the y0 element. So one fewer element than y. Set y. So what does this mean? So we therefore have that the set y minus y0 has k elements. Since we know that y is a set with k plus 1 elements, as we've kind of allowed here. If it has one fewer, we have that this set here has k plus 1 minus 1 elements, so has k elements. Okay, and since we've assumed the truth of pk, so note that this is the induction hypothesis step, so I can write it here. I have the set y minus y0 has exactly 2k subsets. From here, we've assumed the truth here. Let's move on. So let's now consider the subsets of Y that contain Y naught. So let's kind of give it a form. So these are of the form Y naught with set S. So let's define S right now. So where S is a subset of Y minus Y naught. So we've given it this form here. So since we have shown that Y minus Y naught has exactly two K subsets, we could, I guess, say that there are 2 to the K possible choices for S as we've just defined, which implies that 2 to the K, so there are 2 to the K subsets of Y that contain Y naught. So now let's consider the total number of subsets of Y. So since we've split them up in this process here, by separating them by the subsets that contain Y naught and the ones that don't, let's, I guess, combine them now to give this total number of subsets of Y. So let's say the total number of subsets of Y equals, let's do it like this. So the number of subsets containing Y naught with the number of subsets not containing Y naught. And what does this equal? If we look, let's make reference to our earlier working. So let's make some underlines. let's consider the ones that do not contain y naught. And where am I? Here we go. Y minus y naught, which is one we're interested in, has exactly 2 to the k subsets. So that value is 2 to the k. Let's replace this with another color now. So let's look for the number of subsets containing y naught, and that's what we've just recently shown, that there are 2k, or no. 2 to the k. So it equals 2 to the k plus 2 to the k. And this is just some mathematics now. It equals 2 times 2 to the k, which is just 2 to the k plus 1. We're just about done. So this implies that any set y of k plus 1 elements, so let's have a look here. So this is what we've started off with. Any set y of k plus 1 elements has, as we've just shown, has 2 to the k plus 1 subsets. So p of k plus 1 is a true statement. So now we've satisfied both properties. So since we have satisfied properties A and B, we can, I guess, apply the principle of mathematical induction. So this is the grand step. To make a conclusion, so to conclude that, so if we look at what it says, then P of n is a true statement for every n in n. So for all n in the natural numbers, P of n is true. So, in other words, what have we shown in this example? So every set of n elements has 2 to the n subsets.